Now moving on to example 3, we're solving the system by substitution method again. And this time, we're also still solving for a special solution, or a special system, but it is a little bit different. So we want to treat this problem just like any other problem. Step 1, we want to solve for a variable. And in this case, if we look at our equations, equation 1 is going to give us 6x minus 3y is equal to 27, and equation 2 is 2x minus y is equal to 9. So in equation 2, we see that y has the coefficient of -1, so that's probably going to be the easiest for us to solve for. So let's go ahead and solve for that. So we're going to solve for y in equation 2. So we have 2x minus y is equal to 9. We want to simplify y on one side, so we're going to subtract 2x from both sides. Minus 2x is equal to 9 minus 2x. So now our 2x's cancel out on our left-hand side, leaving us with a negative y is equal to negative 2x plus 9. Where now we can go ahead and multiply each term by a -1 to get rid of our negative y. So now we're just going to have a positive y. So we get y is equal to 2x minus 9. So this is our equation. And now for step 2, we want to substitute 2x minus 9 in for y in equation 1. Since we solved for y in equation 2, we're now going to plug this expression into equation 1, where equation 1 is 6x minus 3 times y. So now we have 2x minus 9 is equal to 27. And step 3, we want to solve for x in equation 1. So we're solving for x in this case. So we want to simplify. We have a 3 being distributed into our equations here. Remember, we can also think of our minus 3 as a plus -3. So -3 times 2x is going to give us -6x. And a -3 times a -9 is going to give us 27. So now what we have here is 6x plus -6x plus 27 is equal to 27. Our 6x's are going to cancel out, and what we're left with is 0 plus 27 is equal to 27, where we do get that 27 is equal to 27. This statement is true, but what we don't have is a variable. We didn't actually solve for x. Since our x is canceled out, this means that any value we give for x will make the statement true. So we can say this statement is true. So while the statement is true, this means our system has an infinite number of solutions. And our equations are dependent. So even though our statement is true, we're still not solving for our variables. And this just tells us that our variable, it doesn't matter any value we could plug in for our variable, our statement will always be true. 27 is always equal to 27, and it doesn't matter what we plug in for x, Therefore, it doesn't matter what we plug in for y. So we have an infinite number of solutions and our equations are dependent, which this means that our equations are the same line. So when we want to write our final answer, which is our solution set, when we have this case where we have the same line, we're actually going to write our solution set in set builder notation. And how we're going to write this is that we're going to say that x comma y. So we're basically saying that any ordered pair is a solution to one of our equations, which we can just plug in either equation in this case. But if we plug in the simpler looking equation, plug in equation 2 and say 2x minus y is going to be equal to 9. So this gives us our answer. So whenever we have this case, a reminder, your answer needs to be written in set builder notation. This is how you need to write in these answers when you have equations that are dependent and systems that have an infinite number of solutions. Just like in our last problem, if you would like to check, you can go ahead and solve for y in both of our equations to go ahead and just make sure that your equations are going to be the exact same. And a word of caution, we want to avoid common mistakes such as do not give false as a solution of an inconsistent system. The correct answer is the empty set. So you don't want to write true or false for problems like these. You do have to write out your final solution set. So in the case that it's false, your solution set is the empty set. In the case that it is true, you want to give your answer in your set builder notation. So for number 2, do not give true as a solution of a system of dependent equations. In this text, we write the solution set in set builder notation using the equation in the system or an equivalent equation that is in standard form with integer coefficients having greatest common factor 1 and positive coefficient of x. So in this case, we were just picking one of our equations or equivalent equations and just making sure that's in standard form when we write in our solution set. So when you do write your answer in set builder notation to problems like these, it will always begin with just a ordered pair of x comma y. There will not be any actual values in that case, since we're saying that any value of x or y can be plugged in. So your set builder notation will always look like this, where it has an ordered pair of x comma y. It will have a vertical bar, and then you have an equation that was from your system. Last objective here, which is objective 3, we just want to solve linear equations with fractions and decimals. So example 4, we want to solve the system by the substitution method. Now the only difference is that we have fractions as coefficients instead of whole numbers. But all of our steps will stay or remain fairly the same. So step 1, we want to solve for a variable. But in this case, we don't have any variables that just have 1 or -1 as our coefficient. So what we're actually going to do is we're going to create new equations. I'm going to bring that step down a little bit. So we can create equivalent new equations by getting rid of our fractions. Now the only way to get rid of our fractions is to multiply all of our terms by a number that will get rid of our fractions. So in this case, we have 3x plus 1/4 y is equal to 2. And then we have 1/2 x plus 3/4 y is equal to -5/2. We see our two denominators in this case are 2 and 4. If we multiply each term in both equations in our system, which is what we'll have to do, if we multiply by 2, we'll see we'll get rid of our fraction for 1/2 x, but we still won't get rid of our fractions for 1/4 y and 3/4 y. So let's go ahead and multiply. So we'll multiply each term in our system, so both equations, by 4. And this is going to go ahead and get rid of all of our fractions. This will also give us new equations to work with, equations that will be much simpler for us to solve. We're moving that step 1 down here. So in our equations where we have 3x plus 1/4 y is equal to 2, we're multiplying each term by 4. So with our first equation, when we multiply each term by 4, we're now going to have 12x plus y is equal to 8. And now we're going to go ahead and we're going to label this equation equation 3. So we're going to be working with equations 3 and 4 now instead of equations 1 and 2. Now we're also multiplying 4 into our second equation where we had 1/2 x plus 3/4 y is equal to -5/2. This was our second equation. Keep having to move step 1 down here. All right, so we're multiplying by 4. 4 times 1/2 is going to be 2x. 4 times 3/4 is going to be 3y. And 4 times -5/2 is going to go ahead and give us -10. So now our new system of equations is 12x plus y is equal to 8, and 2x plus 3y is equal to -10. These are equations now 3 and 4. They are equivalents of our original equations. And now we can go ahead and go through all of our steps like normal, and we have equations that have whole numbers now. So step 1, let's go ahead and we're going to solve for y in equation 3. Since we have 12x plus y is equal to 8, we can make it pretty simple on ourselves by just subtracting 12x from both sides. So we're going to solve for y in equation 3. So we'll subtract 12x from both sides. And this gives us our equation of y is equal to -12x plus 8. And in step 2, we want to substitute -12x plus 8 in for y in equation 4. And this is where we had 2x plus 3 times y. So now we're going to have 3 times -12x plus 8, which we're setting equal to -10. In step 3, we're going to simplify. So we're now solving for x in equation 4. So simplifying our terms here, 3 times -12 is going to give us a -36x. And 3 times 8 is going to be 24. So we have 2x plus -36x plus 24 is equal to -10. Combining our like terms, 2 plus -36 is going to be -34x plus 24 is equal to -10. To isolate our x terms on one side, we can go ahead and subtract 24 from both sides. where now we have negative 34x is equal to 10 minus 24, negative 10 minus 24, which is equal to negative 34. So we can go ahead and divide by negative 34 on both sides. And this is going to give us that x is just equal to 1. So there we go. We've solved for one of our variables. So we found that x is equal to 1. Step 4, we can just go ahead and plug in x equals 1 into equation 4 to keep it easy on ourselves. So we're going to substitute 1 for x in equation 4, which our equation 4 was, let's go over here. Equation 4 was 2x plus 3y is equal to negative 10. So we have 2x, so 2 times 1 plus 3y is equal to negative 10. So simplifying, we get 2 plus 3y is equal to negative 10, where we now want to subtract 2 from both sides to isolate our 3y. So we get negative 10 minus 2, which gives us 3y is equal to negative 12, which we can then divide each side by 3. And we get that y is equal to negative 4. So now we've solved for both variables. We got that x was equal to 1 and y was equal to negative 4. And now step 5, we just want to make sure that this is correct. So now we check if 1, negative 4 is a solution of our system. And when we want to check if it's a solution of our system, we have to check the original. So we're looking at our original system. And let's go ahead and make this in red so we really emphasize this idea of original. And our original system, this is really going to mean our fractional system. So when we say our original system, these will be equations 1 and 2. So our equations 1 and 2, remembering our originals were 3x plus 1/4 y is equal to 2, and 1/2 x plus 3/4 y is equal to negative 5/2. So we're going to go ahead and copy and paste this in. So these are our original equations, and now we're plugging our values in. So for equation 1, we're going to have 3 times 1 plus 1/4 times negative 4, which we're stating is equal to 2. 3 times 1 is going to be 3, and 1/4 times negative 4 is going to be negative 1. So 3 plus negative 1 is going to give us 2 is equal to 2. So 1 and negative 4 is a solution of our first equation. Now we just want to see if it's a solution of our second equation. So we're going to have 1/2 times 1 plus 3/4 times negative 4. And we're stating is equal to negative 5/2. 1/2 times 1 is just 1/2. 3/4 times negative 4 is going to give us negative 3, which we're stating is equal to negative 5/2, where negative 3 is the same as saying negative 6/2. So now since we have the same denominator, 1 plus negative 6 will give us negative 5/2, which is equal to negative 5/2. So our ordered pair 1, negative 4 is the solution of both of our original equations. So our final answer, which is our solution set, solution set is our ordered pair written in our curly braces. So that's how we would go about solving a system of equation that had fractional or decimal points as coefficients. So really all you're doing is the same steps that you would do for any other equation. You're just using equivalent equations instead of the originals, just because it would end up becoming very messy by using our fractions or decimal points as coefficients. So you just want to make sure that you get rid of all your fractions or decimals, and then you can go ahead and solve like normal. So, all right, that finishes up our section on solving systems of equations with substitutions. Now in our next section, we're going to be dealing with elimination. So we'll go ahead and I'll see you in our next section as well then.